about UFO, the world listens. He has been interviewed for more books, more TV shows, more radio shows, more newspaper articles, and more websites than any other person in history in our planet. He has been investigating the subject of UFOs since 1958. Mr. Friedman holds undergraduate and graduate degrees in physics from the University of Chicago. A nuclear physicist by training, he has worked for such companies as General Electric, General Motors, Westinghouse, TRW Systems, Aerojet, General Nucleonics, and McDonnell Douglas. His work has included highly advanced and highly classified secret programs, such as nuclear aircraft, fission and fusion rockets, and compact nuclear power plants for space and terrestrial applications. It is an honor to present to you at this time Mr. Stanton Friedman.
Thank you very much. Thanks for coming out tonight. I know there are other things to do in town tonight. Appreciate it. The question of travel to the stars. The nasty, noisy negativists will try to tell you that it's impossible. There can't be any aliens here because you can't get here from there. That's beside the question of why would they come here and all those other silly questions that they ask. But the fact of the matter is, we have learned enough in the last, let's say, 70 years to say that even though we're a very young civilization, I mean, go back to 1900, no flight, no nuclear, no DNA, no radio we're talking about, et cetera, et cetera. But times have changed. We've learned a lot in the last 10 years or so. Now, there are many steps if you want to say, can we go to the stars? Well, which stars do you want to go to? You got a big choice. Our galaxy, the Milky Way, maybe 200 billion stars. It's only 100,000 light years across. There are other galaxies. That's our galaxy, the Milky Way. There are other galaxies, and other galaxies behind those other galaxies. And yet you realize it wasn't until the 20s that we realized there was more than one galaxy. We like to think of us at the top of the heap. We're in the center of the universe. Sorry, we're not. There are, not only is it a big universe, it's an old universe. Very old. The planet's been here 4.5 billion years or so. The universe maybe 13.5 billion years. That's plenty of time for somebody to learn a little bit more than we do. Not surprising if they would. We obviously haven't learned much. As I keep telling people, we're a primitive society. Its major activity is tribal warfare. In case you didn't notice, during World War II, we killed 60 million of our own kind. We destroyed 1,700 cities. Not to be highly recommended on your travel list of nicest places to go to. So when I want to talk about travel to the stars, my favorite location is a place where I think there are other beings. And I have good reasons for thinking so. Two stars you never heard of, Zeta 1 Reticuli and Zeta 2 Reticuli, a constellation of Reticulum, which means the net. And those two stars are a mere 39 light years away. And as I said, the galaxy is 100,000 light years across, and these guys are down the street. But notice the special characteristics of those two stars. They're close to each other. Now, our star, the sun, is out in the boonies. Next star over 4.5 light years, 4.3 light years. These two stars from each other, only 1/8 of a light year apart. From a planet around one, looking over at the other, you can see it all day long. Imagine what that would mean. And also, they've had a little longer time to develop travel to the stars. They're 1 billion years older than the sun. 1 billion. Be kind of neat to go out at night and see a second star there all night long, which they can do. So that's my first choice. And I didn't just make that up out of the air. It comes from the famous Betty and Barney Hill story. That's Barney on the left, Betty on the right, their dog. It's an old picture. The event took place in 1961. I won't go into many details. The first abduction that we've really heard about, not the first abduction, but happened in New Hampshire. got taken on board, examined, tossed back out, told they wouldn't remember what happened, and didn't. Until a couple years later, under regressive hypnosis from an outstanding psychiatrist, it came out under hypnosis that they'd been taken on board, examined. It was pretty terrifying to them. Got treated as specimens. I don't think any of us would like that. But one of the crazy parts of that story is that Betty, under hypnosis, is reliving how she's trying to get the leader to tell her where he's from. I know you're not from around here, she said, understatement of the month. And so the leader shows her what I would only call a three-dimensional star map, maybe a holograph projection. A bunch of stars connected with lines, trade routes, occasional expeditions, some base stars that are pretty close. And Betty, being Betty, she was pretty special. She asked, well, where are you on the map? Wise guy alien says, do you know where you are on the map? No. Well, how can I tell you where I'm from if you don't know where you're at? End of discussion. But Dr. Simon was clever enough to ask her if she could remember what the map looked like. I don't know what he had in mind when he said that, but she said yes. And he gave her a post-hypnotic suggestion. Draw it later on, if you can remember it accurately. And she did, and it's in the book, The Interrupted Journey. And, you know, it's one of those things, what are we going to do with that? A bunch of points that are stars, different kinds of lines. Well, Betty's niece, Kathleen Martin, and I put together a book. She did most of the work. They put my name first because they thought it would sell more. You know those publishers, all they're in for is for the money. And in the book, there's a whole chapter on the star map work. And there's a brilliant woman named Marjorie Fish holding a bust she did of what the aliens looked like, in case you're curious. You can see how long ago that picture was taken in the early 70s. Notice the color of my hair. And I was the first to publish about her work. There's what one of her models looked like, 256 stars in this, each one in its proper three-dimensional location. A lot of tedious work here. And the idea was to look at it from all different directions, see if you can find a three-dimensional pattern that matches a two-dimensional pattern, and get it true. And a lot of work went into it, and here's the names of the stars. You notice the sun. It's very nice that it's on the map. They're here, so presumably it would be. The numbers have changed a little bit because now we finally have good distance data. We used to have lousy distance data because the astronomers weren't going anywhere. What do they care how far away a star is? You can point your telescope at a star with two coordinates. How far does it matter? Only if you're going there. So there's a word up there, Lethe. That's the name of a star catalog. I put together the best data available on how far away the stars are. It's all been taken over, all the numbers have changed a bit because now we have a good satellite up there that made a few million accurate measurements of the distances, and that gives us a chance to really improve on things. And so, Zeta 1 and Zeta 2, we thought they were 34.6 light years. Well, they've been 39.3 light years. So that's my target for tonight. Not 2 million light years, not 2 billion light years, just down the street. So that's the first question. We want to be able to go just down the street to Zeta Reticuli. Now, it's appropriate that you think about sensible ways of doing this. If you want to fly from New York to see your girlfriend in London and back over the weekend, you used to be able to do it seeing the supersonic transport. Doesn't fly anymore, but you could do it then. If you're going to take a cruise ship, it's going to take you 5 days each way, and you can't do it in a weekend. So you have to look at the realistics of the situation. And obviously, chemical rockets, which we use to get to the moon, and all the satellites we put up there, they're chemical rockets. You react to chemicals, they heat up, they go out the back end, out the nozzle, and you go forward. Action, reaction. But we ain't gonna do that if we're gonna go to the stars. Doesn't make any sense to me. Just like you're not gonna walk from here to Houston if you want to be there tomorrow. At least nobody I know would do that. I don't know why anybody want to go to Houston, but that's a different question. Okay. So, the obvious choice, says the nuclear physicist in the crowd, is nuclear energy. Why? Because there's so much more energy per pound of stuff. That's why. Millions of times as much energy. So you go where the energy is. Now, we've learned that, as I said yesterday, about bombs. We know you want to kill a lot of people, you go to a nuclear bomb. Lots of energy. It still fits on an airplane. The same B-29s that dropped the atomic bomb on Japan carried 10-ton blockbusters, energy of 10 tons of dynamite. Well, we upped the ante. That was 44, 45 over at White Sands, first nuclear bomb. About 18,000 tons of dynamite, that's the energy. So we already have a precedent here. Back to the 40s, you want to release a lot of energy, you go nuclear. That's fission. Uranium, plutonium, that sort of stuff. That wasn't good enough for us. So in 1952, we went fusion. Combining two light elements to make a slightly heavier one and converting a little mass to a lot of energy. E equals mc squared. You've seen it in all the comic books and stuff. Well, it's true. If you can find out how to do it. That's the secret. Einstein never thought you could do anything useful out of it. E equals mc squared. Because he didn't know about neutrons. Believe it or not, neutrons have been around all the time we've been here, but they weren't discovered until the early 30s. What's special about neutrons? Well, if you can get a uranium atom to absorb a neutron, you convert a little bit of mass to a lot of energy. Lots and lots of energy. It takes a while to figure out how to manipulate neutrons. But they're all over the place out there. They were there long before we figured out that that's where the energy comes from, you see. And some people don't think that, they think if we don't know how to do it, it can't be done. We're smart people, these professors. And that doesn't always work out that way. The first nuclear chain reactions at the University of Chicago, it was before I went there, I'm not that old, but on the squash court out in the gym, put together the first pile, nuclear pile. Appropriate amounts of uranium and carbon and other things arranged together, and you move a few things around, and you get a chain reaction going. And each neutron, each fission produces 2.5 more neutrons. And each of those produces some fission, so you can see why a chain reaction. You start off with 1, then you get 2.5, then you get 2.5 for each of those, and pretty soon it goes very, very quickly. And neutrons move very rapidly when they're close to each other in the uranium and stuff. Anyway, nuclear fission. And we realized if you could control nuclear chain reactions, you could also produce power. Kind of neat. Yeah, it's tricky. You got to worry about radioactivity and things like that, but there's a price to pay for everything you do. And Admiral Rickover, Hyman Rickover, figured out that, gee, you know, a great use for a reactor, because it doesn't use oxygen, is for a submarine. You know, submarines used to be ships that sailed on the surface and could go down beneath the surface for maybe a day at most, because you need air for the diesel engines. That's beside for the people. It's always handy to have air for them too. But if you got a submarine, you don't need any air. Except for the people, that's easy to take care of. So we built nuclear submarines. First one, the Nautilus, 1956. Loads of countries have built them. Go around the world, underwater. Pretty neat. That's nuclear fission. And as I think I showed you yesterday. Oh, one final chapter, the Betty and Barney Hill incident. The state of New Hampshire has put up a heritage sign right near where the event took place. One of the very few UFO events that's been commemorated officially by the state, even Roswell has. And Kathleen Martin, whose picture I showed you, Betty's niece, had to answer question after question to justify everything that went into that inscription. It took 3 years to get it approved. But there it sits, right outside the Indian Head Inn. And we've had 2 years in a row, we've had a commemorative event there. People come, we take them on a bus tour and so forth. Now, did it again. All right, where did he go? What did I do? See, that was a quick lecture, wasn't it?
You were in a time warp and you went forward in time.
All right, that's the end of this one. How do I go forward?
Is that a wormhole?
Which one are you looking for? What slide?
Well, show me 75 maybe.
Let me see that.
Yeah, that one. Go back. No, forward. Forward.
We're going to go back here, right? Okay.
Yeah, go back. A little more, a little more. A little more. We're getting there. There. One more. No, another one. Another one. Sorry, keep going. We're getting there. We really are. That's it. Okay. I'm sorry. This one. Keep your damn fat fingers off those other buttons. Okay, now you're wondering, what in the heck is this peculiar thing? It was perfectly obvious, once you got a submarine going, that you ought to be able to use nuclear energy for an airplane. What would the benefit be? Well, you have unlimited range, operate for thousands of hours without refueling. You gotta change the crew, but, you know, it's kind of neat. Unlimited range is something everybody would like to have. So you can drop bombs, of course. So when I worked at General Electric, we worked on nuclear airplanes. And the idea was that you would have a nuclear reactor in the middle here, control rods. Air, instead of burning in burner pans, would go through the compressor, go through the reactor, get heated to, 1800, 2000 degrees, and kick out through the turbine. And we have operated jet engines on nuclear power. It's pretty neat. This is what an advanced system would look like. We never did get to the point of really building inside the big airplane. It was exciting at the time, though, operating these things. I was worried about radiation shielding because you really don't want to cook the pilot before he does his mission anyway. So that's what a realistic aircraft nuclear propulsion system would look like. And of course, people worry a little bit, what if it crashes someplace, a lot of radioactivity? Well, we'll be careful how we fly it. How's that for an answer to that? All right, one button. That's a nuclear ramjet. Now that other picture was done about 1958 or so. This is a nuclear ramjet in the early 60s. You put this on board, it gets lifted into the air by a B-52. You carry a few H-bombs on it, and you can release it, and it'll reach any place in the world. Drop bombs. That's what we're good at. This was operated on the ground. It was never flown. Nuclear ramjet. The Aircraft Nuclear Propulsion Department, when I was there in '58, we spent $100 million that year. Employed 3,500 people, of whom 1,100 were engineers and scientists. This was not a little program of 6 guys around a table figuring out how they could do this on paper. We built a lot of hardware. Spent a lot of money. Your money. And $100 million is a lot of money back in '58. It isn't that. It's peanuts, but, you know. But these are within the atmosphere. What we really like. Here's a schematic of what a nuclear fission rocket reactor propulsion system would look like. Hydrogen comes in, cools the control rods, you don't want them to melt, goes up through the reactor, leaves at about 4,000 degrees, no oxygen in this thing, a little over 4,000 degrees, and the system, about 7 feet in diameter with operating power level about 1,000 megawatts. A big dam produces 2,000 megawatts. The big brother of this one, this is just a schematic, but we built these things, they're real, would produce 4,400 megawatts. Twice the power of Grand Coulee Dam. How's that something this big? That's nuclear energy. If you put this on the upper stage on a rocket to go to Mars, let's say, you can triple the payload, which is kind of attractive, because the bigger the payload, the more you can do to set up a place and so forth. Now, this is ours. I worked at Westinghouse Astronuclear Lab, and I did work on this. Reactor in here, nozzle. It's on a railroad car because it gets radioactive, and you've got to send it remotely back to the assembly and disassembly building. You don't want to stand around this thing while it's running, to say the least. This is real. 1968, only 1,100 megawatts. Westinghouse Astronuclear Lab, and I was there, and I had some experiments going on it, and it was very exciting to sit and listen over the PA system at Westinghouse. We had a special setup as they were operating, and the question was, how long would the thing last before it came apart, if we were being honest with each other. The maximum time it could operate was 1 hour, because that's all the liquid hydrogen we could store, because once you've finished operating this thing, it's still radioactive and hot, and it needs cooling. And you really do want to cool it because you don't want it to go splat. And boy, it was exciting. 20 minutes, 30 minutes, 40 minutes, all temperatures what you want them to be. 50 minutes, 60 minutes, we went to full time. And of course, then the program was canceled. What can I say? Because nobody had guts enough to plan for it in a system. That's what my life has been, failed government-sponsored research and development programs. Now, Los Alamos, there were 3 companies involved in the nuclear fission rocket business. Westinghouse Astronuclear Lab, Los Alamos National Laboratory, and Urja General, out in Sacramento, was their home base. This is Los Alamos' Phoebus. This was the small one. Their big one, I think I have it here. No. Oh. The big one's a little bigger than this, about 8 feet in diameter, 4,400 megawatts. Very impressive. And if you think we were just talking about building these things, here's one in operation. Area 51 is on the other side of those mountains. And those little white tanks there are tanks of liquid hydrogen, which of course some people said, oh, you couldn't possibly operate a reactor on liquid hydrogen. It's explosive. There were cities that had laws against storing gasoline there back in the late 1800s, early 1900s, much too dangerous. And every once in a while, you'd have a fire at a gas station, you know. Some people store gasoline in their garage, and every once in a while, they might have a fire. But this is real. Like I said, you don't want to be standing close to one of these things when it's operating. A lot of energy in a small place. There's a conventional nuclear power plant in New Brunswick, where I live in Canada. Its power output is about 2,200 megawatts. This thing was operating at 4,000 megawatts. The reactor's a great deal larger. So we're making progress here in other areas. It says here, before the program was canceled, of course. So this is a variety, then you get an idea of the size of these things, the power level, the thrust level. This is an upper stage now. You're not going to launch from here. And it's a little safer to get it up on a chemical rocket and light it off up there. We do worry about safety, we nuclear guys, most of the time. Now this is nuclear fission. That's what goes on in the Navy systems, in the 400 and some power plants there are in the world, nuclear power plants. But that's not the next step. Oh, this is the Urja one. That's a flight-ready system, downward firing. And you got to cool that chute that the exhaust goes down. A lot of energy. other uses of nuclear energy, the Pioneer spacecraft, for example, used radioisotope thermoelectric generators. Use nuclear energy, plutonium-238, heats a place, and there's a law of physics. If you got a hot end and a cold end, use the right materials, you got a current flowing between them. So the Pioneer spacecraft, these things run for 30, 40, 50 years. And as you can think, why not solar? Well, because the further you get from the sun, the less solar energy there is. You know, think about that for a while. So we're heading toward Pluto now. It's got a nuclear radioisotope thermoelectric generator. I worked with some of these. They're kind of nifty. Some people get scared. The one that's sitting out in Saturn now, we sent it past Venus to get a free kick, to send it past Earth to get another free kick, to go past Jupiter to get another free kick, and headed toward Saturn. And people were screaming, it's got plutonium on it, you don't want that in the atmosphere, and they were hiding under the couch kind of thing. It's not plutonium-239, which you make bombs out of, it's plutonium-238. And of course, nothing happened. Some people got their moment in the sun, I guess. And we have a whole bunch of these. Everybody does, except we're running a little short of plutonium-238. Here's what they look like. The plutonium in the middle there. These are really pretty neat. And there are loads of them up there producing electricity for years and years and years and years. Which is kind of nice. There's a nuclear submarine. And they go around the world underwater, doing their thing. And, you know, the funny thing is that we had nuclear submarines before somebody thought, you know, we could put a rocket on those Polaris missiles. And if somebody attacked us, they wouldn't know where we were to attack them back. Mutually assured destruction. Doesn't that sound crazy? Mad. You hit us, we'll hit you. We'll both be dead, but that doesn't help you and it doesn't help me. So what is interesting is that the submarine existed before we had the idea of putting a nuclear-tipped missile on board. People can be creative. And this is one of my favorite slides. That's a nuclear-powered aircraft carrier. And this is the one that operates for 18 years without refueling. Think of how many shiploads of diesel fuel that would be. You know, in war, it's hard to get fuel. And so all your maneuverability of your fleet and everything is determined by the big ships carrying fuel for the smaller ships. And you can't go real fast because that uses up fuel a lot quicker. Nuclear powered, you can go full steam ahead as long as you want. Which is kind of nifty. And most people don't know that we have 18 years without refueling. You know, so some airplanes, they can operate for 2 hours. So I like to talk to people, if we're talking about going to the stars, we've got a system to get from our solar system to their solar system. And once you get in the solar system, then you got your little airplane, so to speak, an Earth excursion module, to run around in the atmosphere. A two-stage system is the way we do things. Obviously, the carrier doesn't work worth a darn in the air, and those little planes don't work worth a darn on the water. You got to specialize a little bit. You got to think about what you're doing. So this is nuclear fission. It's a step in the right direction. It's not the big step we want. That's our first H-bomb, 3-mile-wide fireball, 1952. Released the energy of 10 million tons of TNT. That's a lot of oomph. The Russians, their biggest one was 57 megatons, million tons of TNT. That's an incredible amount of energy to be able to have at your control in one bomb, which they did. But that means what you're using is nuclear fusion. And most of us don't talk about nuclear fusion, but everybody in the universe knows that their star works by nuclear fusion. That's the process. And the fuel is hydrogen, which is very nice because it's the lightest and most abundant substance in the universe. Now you need uranium in the fission plants. Uranium's heavy, 19 times as dense as water, almost twice as dense as lead. Hydrogen is as light as you can get. That's an attractive feature. And it's all over the place. No matter where you go, there are gas stations for hydrogen. All over the place. Now, as it turns out, there are a lot of fusion reactions. I've selected a few of them here. Don't be scared by that looks like an equation. It sort of is, but don't be worried about it. Here's the important thing. If you pick the right fusion reaction, you can produce charged particles. You say, so who cares? Well, if you got charged particles, they can move out the back end and be directed by electric and magnetic fields. And so they're all going that way. If you produce neutrons, they go off in all directions. That doesn't do you much good if you want to go that way and they're going this, that, and the other way. Now, here's an idea of the amount of energy that we're talking about here. In that top equation, where am I pointing this at the screen? 18.3 million electron volts. That's what that means. This is helium, heavy hydrogen, deuterium, proton. Now, million electron volts, what does that mean? Your normal reactions, if you light a match, you light a cigarette, you burn gasoline in your car, they produce a few electron volts per reaction. Each fusion reaction of the right kind produces 18 million electron volts per reaction. A big, big multiplier. So if you pick the right stuff, you can get particles out the back end that have just about 10 million times as much energy per particle as you can get in a dumb old chemical rocket. Not 10 times, not 10,000, 10 million times. I worked on a study of nuclear fusion for deep space propulsion back in the early 60s. If you use the right stuff in the right way, 10 million times as much energy per particle going out the back end. Now, it's going to be expensive. Controlling fusion reactions is not cheap. Why would you expect it to be? And I'm not saying we should spend the money. But remember that just to build the first A-bomb cost a few $1 billion in 1944 money. So nuclear fusion looks very attractive for deep space propulsion. Pick the right systems, and away you go. Now, you're not going to use it down here, because you don't need to go close to the speed of light down in the atmosphere. But between the stars, they're kind of a long distance compared to the size of the planet. Fusion would do the job very nicely. There have been a number of studies. I found them very exciting. Head of our program at Aerojet General Nucleonics had been in charge of the fusion work at Oak Ridge National Laboratory. But this work is generally not done at universities. It's done at national laboratories, which employ thousands of people, and about whose work you know very little. The total budget for the 3 nuclear weapons labs, all of which have done some fusion work, was more than the total budget of the National Science Foundation for everything it did a few years ago when I checked on this. So, are we spending money on nuclear fusion for deep space travel? Very little, because nobody's decided we want to do that. Where are you going to go? What are you going to go for? Nobody's given us an invitation. Who would want us out there? As I keep saying, we're a primitive society whose major activity is tribal warfare. We're not nice guys. We build nuclear weapons to kill people with. That's what they're for. We have exploded 2,000 nuclear weapons on this planet, fission devices and fusion devices. 2,000. Only 2 of them on people, for which I am eternally grateful. And so should you be. One of the major wonders of the last, let's say, 60 years, is that there haven't been nuclear weapons dropped on people, even though there are thousands of them running around, or there to be used. There's a guy named Robert Hastings who's done a book on nukes and UFOs, showing that they're very concerned about nuclear-tipped rockets and stuff like that. They're sending us signals that we don't like that, guys. 10 Minuteman missiles went down, one after the other, at Malmstrom Air Force Base. That can't be done, but it happened. And there was a press conference in Washington where a number of the military people were involved in some of these places where the nuclear things were interfered with, have told their stories. Some people it doesn't seem to bother at all. So fusion is really the way you want to go. Now, am I insisting that that's the ultimate energy production device? Of course not. Progress comes from doing things differently in an unpredictable way. The future is not an extrapolation of the past. A fusion system is not just a better chemical rocket, entirely different physics. A nuclear submarine isn't just a regular submarine. Entirely different reactions going on. The same with the aircraft carrier. So, I can even think of some ways in which you could produce other possibility, quarks and stuff like that. But let's not worry about it. Everybody in the universe will know about nuclear fusion, because that's what produces the energy of the stars. All of them. There's not many things that you can say all. But all the stars, billions and billions, operate by nuclear fusion. There are different temperatures, different this, that, different that, but all variations on the fusion style. And it is interesting. You'll see those D's up there. Any of you do crossword puzzles regularly? One of the things you find in a crossword puzzle, 4-letter word for the discoverer of heavy hydrogen, U-R-E-Y. Dr. Uriarte was the scientist who discovered that in 1932. And that it's a crucial reaction. Only 1 part in 6,400 hydrogen atoms in the ocean is a heavy hydrogen one. Only 1 part in 6,400. But we're glad it's there. And it's important in the sun. This is stuff nobody tells you about. And some people are anti-nuclear. There are anti-protons. That's a kind of particle. But anti-nuclear is another whole ballgame. So, fusion reactions will get us to the stars. Now, there's another part about this star travel bit. You hear many people say, well, what's the matter, Friedman? You don't know about Einstein? You can't go faster than the speed of light. Look how long it's going to take you to get any place. Well, I've tried a little gambit when I go to college campuses. Oftentimes, they invite me to give a program in the afternoon, a little seminar on flying saucers and physics, and I find out from the students that the professor's going to show me up and how stupid I am. So I love those occasions, because I make sure I talk about things that I know they don't know anything about. Oh, you're all familiar with the electromagnetic submarine. I'll show you one in a minute. Well, no, they aren't, and a whole bunch of other things. And pretty soon the kids realize that professors don't know as much as they think they do. But then I get a little sneaky. It's worth it. I'll say, because the other part of that, what can't be done, is the acceleration. Be smashed to death by the acceleration. One book, Physics for People Who Don't Think They'd Like Physics, I don't like the book, is when you get to 9 Gs, you die. 9 Gs, you die. That's total baloney. Well, if you hit a wall while being accelerated at 9 Gs, you die. But why would you do that? Now, how many Gs can you stand? Well, that's what I ask the students. I'll say, first of all, what's the numerical value of 1 G? 9.8 meters per second squared. In which I say, well, we don't measure anything else in those units. How do you relate that to a Corvette? My acceleration car, you know. And they look at me like I'm talking Swahili. They don't want to think in terms of the real world. Well, as it turns out, 1 G, 9.8 meters per second squared, is about 21 miles per hour per second. So if you're accelerating a car at 1 G, at the end of 3 seconds, you're going 63 miles an hour, and you get a pretty hot car. Because most cars will take 5, 6, 7, 8 seconds to get to 60 miles an hour. And then I ask them, well, okay, what's the speed of light, the numerical value? 300,000 kilometers per second, they all know those numbers. I say, well, how do you relate that to the real world? And again, they look at me like, what are you talking about? It's about 670 million miles an hour. And dimensions in the solar system are hundreds of millions of miles. So Jupiter's, less than a light hour away, if you want to put it in those terms. And then after I told them that, I said, okay, now I got the key question, multiple choice question for you. How long does it take at 1g acceleration to get you to the speed of light? It's a multiple choice question. 1,000 years, 100 years, 10 years, 1 year. How many think it's 1,000 years? Hands go up at 110 and 1. The right answer is 1. 1 year at 1g acceleration gets you the speed of light. At 2g is half a year. And that's kind of a kicker, isn't it? Because they want to forget the other half of Einstein. Speed of light's the limit. But he also said, which has been proven by experiment many times, we have to take it into account when we build these huge accelerators, as you get close to the speed of light, time slows down for things moving that fast. Don't ask me why, that's the way God created the universe. You're going to look at it that way. But it's true. Well, how much do you slow down? Well, at 99.9% of the speed of light, 99.99% of the speed of light, you can go 37 light years in 6 months, pilot time. Pilot time. That's kind of neat. You go out, come back, marry your granddaughter's best friend. This is real physics. This is not fun and games. Now, that Large Hadron Collider out in Geneva, well, in Switzerland there, the particles in there go 99.99999% of the speed of light. So we know something about having things going close to the speed of light. So you're going to take advantage of that. Obviously, if you're a good engineer, you do whatever it takes to work within the laws of physics, but get your engineering goals achieved. That's what life is all about. Any engineers here? Oh, we got one. Good. I had more fun working with engineers than with other physicists. So when you start putting these things together, you see that, well, wait a minute. In the first place, how come those professors didn't know that it only takes a year at 1g to get to the speed of light? Why did they think it was 1,000 years? Because they don't live in the real world. Because it doesn't matter to them. We make particles go very fast. And, you know, people ask me, are you sure that's right? I say, when we build accelerators, we have to take into account the slowing down of time as you get close to the speed of light. It's not an imaginary construct. It's something that's part of the world in which we live. There are cosmic rays coming here from out there somewhere that go at 99.99999% of the speed of light. We don't make them. You don't want to get hit by them either. But so we suddenly realized that it isn't that big an impossibility. Now, I should tell you about Dr. Campbell. I mentioned him the other night, but to illustrate how to go wrong with smart people. He was an astronomer. He was sick and tired of all these people talking about going to the moon in 1941. Science fiction, of course. Men would never go to the moon. We all know that. Then. We don't know that now. And he figured out, he wanted to show them up. What a stupid notion. Published a paper in a scientific journal. What would be the required initial launch weight of a rocket able to get a man to the moon and back? Legitimate question. How big? Pages of equations. Bottom line, it would have to weigh 1 million tons. And in case you didn't know it, when we went to the moon with the Apollo system, the Saturn V rocket, it weighed 3,000 tons, and we got 3 guys up there. How could he be so wrong? Because he made every wrong, stupid assumption you could make. He assumed a single-stage rocket. We don't use single-stage rockets. The big booster, when you get rid of it, throw the can away. Why are you carrying it around? Second one, same thing. He assumed that when you're coming back from the moon, you got to slow down. That's a good idea because you're starting at 25,000 miles an hour. Good way to dig a hole in the ground. It turns out that if you're smart, he thought you'd have to use a retro rocket. which does nothing. You carry it up to the moon, you gotta lift it from the Earth, you gotta slow it down at the moon, you gotta lift it off from the moon, then use it back here. Well, why would you do that? What do? We say, thank you, God, for giving us an atmosphere, gives us something to breathe, which is kind of handy, and we can use it to slow it down if we're smart. Remember Apollo 13? You got to get the angle right when you're coming back. Too steep and you dig a hole in the ground, that's not very comfortable. Too shallow and it's bye-bye Earth. But if you get it right, and it's much more important to be smart than it is to be strong. Makes a huge difference. He assumed the rocket would have to provide all the energy. Of course it would. Well, how else are you going to go any place? That's like saying if you want to go from here to Boston, you got to carry all the fuel in your car for the trip. Well, why don't you stop and get gas along the way? Not a bad idea. That changes the size of the system rather enormously. He also assumed that you had to provide all the energy, but he forgot something. The moon you're going to has a gravitational field. We sometimes forget that, but if you launch at the right time, the moon will come along at just the right time, very reliable, and pull you in. No expenditure. Clever, huh? He assumed too low an exhaust velocity. He assumed a limit of 1 g acceleration. Well, how many g's can you stand anyway, Stan? It depends. A trained pilot can perform a tracking task while being accelerated at 14 g's for 2 minutes. That's 300 miles per hour per second. Think about that for a minute. And now, the force better be in the right direction, back to front. You ever notice how the astronauts go up on their back when they're put up in space? Why is that? Because the body can stand a lot more force back to front than foot to head. Those joints don't like high G acceleration. But you got to do what's sensible. You don't limit where you don't have to limit. You take advantage of Mother Nature. The astronauts routinely take 5 Gs. There's a little rocket on top of the command module, which will subject them to 13 Gs. If you got to get them off the rocket because there's a fire down there and the rocket isn't working and you want to get the heck out of there before it blows up, 13 Gs, that rocket will get you the heck out of there. And sure, you're not walking around drinking a beer, smoking a cigar, you can't have had 3 heart attacks. There are limits. But if you do things sensibly, you can get what you need by taking advantage of our knowledge of Mother Nature. It's kind of like Felix Baumgartner the other day. You notice he was launched from Roswell?
Yeah.
Pretty neat. And, you know, if you offhand say, would you jump out of a balloon at 120,000 feet? What, are you crazy? No, he did it. I found that exciting. Not just because it was Roswell, but it was well planned, well thought out. And the guy, the old guy who was there, was the guy who had the previous record, Joe Kittinger, was a crackerjack pilot. He made one mistake in his life. When they were trying to get rid of Roswell, some of us have heard stories about red-haired officers. And Joe had been red-haired. So he came forward. Well, that was me. I was at the hospital at the base, had an accident out there. And so I must be the guy. He didn't bother to tell you. That happened in 1959. Roswell happened in 1947. So we have crash tests. Crash test, yeah. We have redheads that time travel from 59 to 47. But I got to give the guy credit. I don't like when he said that, which was a stupid thing to say. It wasn't him, of course. But the guy's one heck of a pilot. Flew loads of missions in Korea during the war. He's in his 80s now. And I was very glad to see that he was being the planner for Baumgartner. Now, I wouldn't want to do that, incidentally. I don't care who was doing the planning. I don't know how many of you would like to jump out of it. Yeah, you know, that's a pretty memorable picture. A guy up at 120,000 feet and leaning forward and diving. Now, impossible, you can't do that. But he did it because it was well planned. Good engineering work, good solid. One of the early tests about pushing people out of dummies out of rockets, we tried some live ones, and it was discovered if you go out of an aircraft at 42,000 feet, you better not pull your ripcord right away. You'll freeze before you get down. So you got to learn to free fall. Now, nobody would have talked about falling. What did he get, 860 miles an hour? 840 miles an hour, something like that. Anyway, it's crazy to do that, right? It's impossible, isn't it? Well, not if you plan it properly. And so, it takes good planning and good solid engineering. And you got to know your parameters. You got to know what you can stand and what you can't stand. And, you notice that Felix Baumgartner is not 87 years old. There are limitations about all these things. So, okay, let's get away from nuclear fusion and stuff. Oh, Dr. Michael Shermer, he's a skeptic. I debated him. I got 80% of the vote on George Norrie's show. Because he didn't know what he was talking about. That's par for the course for debunkers of UFOs and space travel. He said a lot of other stupid things besides it about UFOs. There's Frank Drake. Now, I have a certain amount of respect for Frank. He shows what is called the Drake equation. Now, anybody who knows anything about mathematics knows that it isn't an equation. It's not an equation. You can put whatever numbers you want in and get whatever numbers you want out. Like, what's the lifespan of a civilization? Anybody know? I don't know if anybody knows that. Well, Frank he's the first guy who did a radio telescope search for extraterrestrial intelligence. SETI, big shot in the SETI Institute. As I keep saying, silly effort to investigate. He assumes that, gee, there might be as many as 8,000 planets in the galaxy from which signals could be sent. Now, why anybody out there would send signals to this primitive society whose major activity is tribal warfare, I don't know. Remember, they'd have to use technology appropriate to us. We've had long-distance radio communication for 111 years. They could have been going around for millions, billions of years. I mentioned Zeta Reticuli. Those two stars just happen to be a cool billion years older than the sun. What's a billion between friends? You know. So, the Kepler satellite, which is a remarkable device, it's in an orbit, a long orbit around the Earth, looking at a chunk of the sky about this big, a fist at arm's length. People say, why doesn't it go listen to Zeta Reticuli? It can't. It can only go in this orbit. And it's so sensitive that it can catch the flight of a planet in front of a star, like seeing a butterfly go in front of a car headlight at a mile away. It's an incredible device. And we've already discovered lots of planets. They're all over the place out there. And so, SETI is kind of out of date. Now you can go see the Large Area Radio Telescope over in New Mexico. That's where Contact was shot. And Jill Tarter she was the model for the woman in, she just quit her job because she turned 68 at the SETI Institute. Now she's just going to raise money. She's not listening for signals anymore. And I did a column for one of my monthly columns showing how silly the thing was she said about when you're so close to the ultimate choice, the incredible thing when we get a signal. I think most people will say, oh, did you hear they got a radio signal from someplace? That's nice, Joe, pass the butter. If you say, oh, there was a landing of a saucer 2 miles away and they kidnapped 3 people and never brought them back, now you're going to have an impact. That's going to matter. So Frank's a good guy, but he has said some dumb things, really dumb. And this whole business of radio signals. Now, think about it. I don't use a slide rule anymore when I do my calculations. Some of you know what a slide rule is, I hope. I had 2 classes of students at a university, and none of them knew what it was. It was a way to do fast calculations, non-electrically, like a ruler and so forth. I still have them. They have them in museums. Dennis probably still has one, don't you, Dennis? Well, you know, think of your pocket calculators and so forth. We don't do things the way we used to do them. Progress comes from doing things differently in an unpredictable way. That's the law of the universe as enunciated by me. Nobody's called that Friedman's law yet, but anyway. So Frank's a good guy. He's a little older than I am, but that's all right. But the Drake equation doesn't really tell us anything because we don't know what numbers to put in.
I'm sorry, second?
What?
Second? You don't know how numbers to play in there, so how the formula came in?
Well, we don't have values. You know, the average distance between stars, we don't know. What's the lifetime of a civilization? We know about one civilization, if you can call this a civilization. How long is it going to last? We don't have any idea. You know, so you pick your numbers. This goes back to that acceleration business. And it's something that's very often misunderstood. How many G's, how long you can stand it in seconds, the 3 different directions, back to front, front to back, foot to head. And it matters. The body is constructed in such a way that it matters. So this is the trained pilot, 14 G's for 2 minutes. Actually, for a short period of time, you can stand 30 G's for 1 second. And a guy was running experiments. He was on a sled that you accelerate up to high velocity and then slow down in great hurry. He took 43 G's for less than a second. Lived to tell the tale. His eyeballs were uncomfortable. It's the price you pay. So we know something about how many G's we can stand if you're healthy and so forth. And you know, one of the funny things is we've never been able to predict who could handle 0 G. You know, they send the guys up in the vomit airplane. They go into free fall, fire the rocket, turn it off. And some people get sicker than a dog and other people it doesn't bother at all. And we've never been able to predict who's going to get sick and who isn't. I'm not volunteering for these experiments, you understand? But, so G's are part of the picture.
So it is algorithm.
Hmm?
It is algorithmical
For the ballistic? Yeah. Here's an electromagnetic submarine. And people say, what the heck is that? No moving parts. It's kind of nifty. It's a law of physics. We don't often use our laws of physics, you know. But when you have electric and magnetic fields at right angles to each other, you have a force at right angles to both. If you push against an electrically conducting fluid, seawater, by Newton's law, it pushes back. Nature is very cooperative when you understand how it works. The idea is to produce the electric and magnetic fields. And so Dr. Stuart Way, EMS is Electromagnetic Submarine 1. Japanese built one too. Dr. Stuart Way, Westinghouse Research Lab, a world-class expert on magnetoaerodynamics, with a bunch of grad students at the University of California, Santa Barbara. They built one of these things and it worked. No moving parts. Dr. Way in the middle. They spent $2,000. If it had been done in industry, so it would have been $200,000, all right, but a little for overhead in there. There was an article in Time magazine, there have been technical papers produced about this stuff. This is real, I'm not making these things up. For those of you who want equations, they're available, you can calculate stuff. But it's a whole different means of motion. You say, Stan, what's that got to do with flying saucers? They don't work under the water? Well, sometimes they do. There's over 1,000 reports of saucers coming into or out of the water, which is kind of nifty. But the idea is that seawater is an electrically conducting fluid, and if you ionize the air, it's an electrically conducting fluid. And you can interact with electric and magnetic fields. You can control heating, drag, sonic boom production, radar profile, all kinds of nifty things. Is anybody doing that sort of stuff? Well, back in 1970, when I worked briefly for McDonnell Douglas, I had a literature search done of government report literature using one word, keyword, magnetoaerodynamics. I got 900 references. 90% were classified. Somebody was paying attention to ionizing the air and interacting with electric and magnetic fields. Now, you may be vaguely aware, if you remember, when we came back from the moon in the Apollo command module, we lost communication for a while, because when it hits the atmosphere at 25,000 miles an hour, it ionizes the air. That goes around the craft, and you can't get the electromagnetic waves through that ionized air. So we produce plasmas. And it's very important if you're going to send a missile to land in somebody else's backyard, the drag in the atmosphere depends a lot on things like how electrically charged it is and the plasma it makes and all that sort of stuff. So that was one of the reasons we spent a lot of money working on that. If you're going to fire a missile to clobber somebody, you want it to go where you want it to go. It isn't enough to just, well, shoot it up and see what happens. Although, as I think it was mentioned earlier today, some of the rockets fired at White Sands landed in Mexico. Not intentionally, but things do go astray. Okay, electromagnetic submarine. Now, one of the big arguments made against going to the stars, the Fermi paradox. That's Enrico Fermi. One of the reasons I went to the University of Chicago, switched from Rutgers, was because Fermi was there. He was the first guy to do a nuclear chain reaction. When a Nobel Prize winner from Italy, before the war, did all kinds of experiments with neutrons and then was in charge of the first nuclear chain reaction at the University of Chicago. And he was a scientist. You can't believe, I was at the university when he died. You can't believe what other top-notch scientists said about Fermi. Brilliant man and an experimentalist and a theoretician both. That's rare, that combination. Now the Fermi paradox, so the story goes, is as he and others were eating lunch at Los Alamos, they figured out that, once you got started, you ought to be able to colonize the entire galaxy in a couple million years. Well, we got billions of years to play with, so no big deal. As they're leaving the cafeteria, Fermi says to the other guys, "So where is everybody?" They all know what he meant. He didn't say there's nobody there, or nobody coming here. He asked a sensible question. And he was famous at Chicago for teaching by asking questions. The sky is blue, figure out somebody's third law, this or that. Brilliant man. But there are whole books, answers to the Fermi paradox. Now the noisy negativists will all tell you, well, Fermi said there's nobody coming here. No, he asked, where is everybody? A lot of different answers. I don't know where everybody is, but one of the answers might be they're coming here and our government knows about it and it's not telling us about it. That's where some of them are. And there are all kinds of explanations. But the guys who want to not think but react will say Fermi said that there's nobody coming here. He didn't say that at all. And I have, it's one of the ironies of World War II. Fermi's wife, Laura, was Jewish. When he went to get his Nobel Prize in Oslo, or wherever, where did they get? Stockholm, I guess. They went there, and then they went right on to the United States because, this is 1938, Mussolini was becoming a little Hitler when it came to how he treated his Jews. So here we have the guy who was in charge of our atomic bomb program over in the United States, along with a lot of other top scientists, because Hitler was a blankety-blank blank. That seems, he got what was coming to him, kind of thing. But don't let anybody kid you that Fermi, the brilliant Fermi, and he was brilliant, showed that there was nobody coming. That's not what the case was at all. Oh, I talked about this. Project Blue Book Special Report 14, biggest study ever done, 3,201 sightings, 21.5% were unknowns, but the Secretary of the Air Force said even the unknown 3% could have been identified as conventional phenomena or illusions of more complete observational data than available. An absolute and total lie. If you look at the data in the report, 21.5%, not 3%, completely separate from the ones for which there wasn't enough information. And not one newspaper caught the lie, and the statement was all across the country, 1955. Don't always believe what you see in the press. Now, here's his statement. You can read that. Again, a total lie. I don't like being lied to by the Secretary of the Air Force. And my classmate Carl Sagan said, another lie. The reliable cases are uninteresting, and the interesting cases are unreliable. Unfortunately, there are no cases that are both reliable and interesting. No basis is given for this totally false claim. Don't bother me with the facts, my mind's made up. There's Carl. Here's the breakdown of all the sightings. You notice it says psychological in the middle there. Really, it was psychological manifestations, but that was too long to fit there. And I got some people saying, well, you heard it a month ago, Dr. Rees, the British Astronomer Royal, only kooks see UFOs. Basis given? None. Personal, idiotic opinion, frankly, because you can find lots of sightings by people who aren't kooks, like other astronomers, like pilots, like engineers and scientists, and so forth. And notice the second line from the bottom, insufficient information. And incidentally, I'm always glad to say that the American Physical Society says that 2% of the papers submitted to it by physicists are crackpot papers. There are more crackpots associated with physics than with flying saucers. Only 1.5%. Here's the quality evaluation. Remember what Carl said? Well, as it happens, the higher the quality, the more likely to be unexplainable. That's the fact, not the mythology put forth by the noisy negativists. Leslie Kane, she's a darn good journalist. This has got all kinds of testimony from military leaders in a bunch of countries who have seen flying saucers, I might add. You all remember told me, well, it was a couple thousand years ago, but pretty close. He's the guy who said the Earth is the center of the universe. No basis given, but it was pretty obvious if you go outside, everything goes around the Earth. We all know that, you can see. The sun goes around the Earth. Of course of the day, it's over there, then it's over there. Obviously, we're the important part of the universe. Then Copernicus, he said, no, the sun's the middle of the universe. My joke for the day, the St. John, New Brunswick newspaper, Telegraph Journal, did this cartoon in my honor. They'd run an article saying I was inducted into the UFO Hall of Fame over in Roswell. I get kind of a kick out of that. A whole bunch of books. I only have some of them over there, but I want to leave time for questions. Let's summarize. Is it going to be easy to get to the stars? Of course not. Was it easy to get to the moon? Of course not. We did it in spite of the noisy negativists. Was it easy to build the first nuclear submarine? No. A lot of work. I'm not saying it's easy to get to the stars. It's a big effort. Remember, the Manhattan Project involved 60,000 people at one time or another, and a few $1 billion in 1943 dollars, which was a lot of money. In case you're interested, incidentally, when I talk about money, at Oak Ridge, there was one facility that was built during the war. It was a mile long. Its purpose was to enrich uranium. You pump uranium hexafluoride gas through little holes and nickel barriers, and the lighter one goes through faster, U-235 versus U-238. that facility was using 5% of the electrical power produced in the United States. 5%, in secret. And the reason it was in Tennessee is because of TVA. They were producing lots of power there. And they were using it for this facility. Things can be done that are quite remarkable and that we don't know about. I'm sure that surprises everyone. Here's one of my books. There's another. Oh, sorry. There's a UFO, just to show you that there are some good pictures. Taken in Brazil, released to the public by the President of Brazil, one of 4 pictures taken by an official Brazilian Navy photographer. We're not going to go there. Let me go back. Thanks for listening. Does anybody have any questions? How to get rid of the flies? I don't know.
Okay. Are you excited about the privatization of space travel?
About the what?
Privatization. The private companies.
Oh, privatization.
Yes.
Well, yes, I am, to tell you the truth. When I was working in the space business in the 60s, all of us thought we'd be on the moon by now with
Yeah,
a base.
right.
We thought we'd have gone off to Mars.
Yes.
What's been missing is vision, to use that George Bush expression, that vision thing. Leadership. Since Kennedy said, let's get a man to the moon and back by the end of the decade, NASA hasn't had a goal other than to spend the money that comes their way. And I worked on at least 5 different programs that needed somebody with vision. That's where we're going. And you don't want to go there, get off the train. That's what Rickover is all about. And there's another irony there. I mentioned about Fermi and his wife being Jewish. Fermi wasn't, his wife was. Rickover knew that he would never become a full admiral. So his job was to be the best engineer he could be. And that was because he couldn't join the country clubs,
Yes.
all the things. The times have changed. But somebody who says, Werner von Braun was a leader. I hate to give credit to somebody who was a Nazi for some of the time, but outstanding leader, inspired other people. That's what it takes. And Rickover used to say he always hires people smarter than he is. Not everybody has guts enough to take that attitude, but he did, and we had the nuclear navy first. That's a good thing, very good thing. No, I think privatization would be great. As a matter of fact, I know Bob Bigelow, who's got a system up there. He's a billionaire from Las Vegas. And there are several guys in the private space business. And these are the guys who are going to get us ahead. If the government ran the computer business, you'd have your choice of 4. They'd all be about the same. They cost 3 times as much as what we're spending now. The thing about private business is the right to fail.
Yes.
That's a terrible thing to say, but it's true. There has to be a reward, and if you can't cut it, too bad. Sorry, somebody else will come along and do it. Who can cut it? Questions? How many of you have seen a flying saucer? There's one. Usually, I will have to tell you this. Usually, if I have 500 people out there, I'll ask at the end of the lecture, how many people here believe they've seen what I would consider to be a flying saucer? And I'll say, we didn't let the CIA in, just raise your hand and I'll point and count. And so 1, 2, 3, 4, 5. The hands are just barely over their heads, you understand. Each one thinking he's the only one. By the time I get over there, the hand goes up like this. 10% of the audience believe they've seen one. But then I ask, how many of you reported what you saw? 90% of the hands go down. If there's still anybody left, I'll ask, how many of you were in the military at the time? A little tricky. And if there's still some hands, I'll say, you want to tell us about it. One guy here in Texas, in front of 1,300 people at East Texas State, I can't, they told me not to say anything. Wonderful line. Couldn't have been better, Up in Indiana, in Indianapolis, I went through that sequence, and a guy asked, you want to tell us about it? They took my pictures. Long silence.
What?
Everybody's wondering. I said, well, look, I'm not going to ask you your name. You don't need to stand up. But I'm sure the audience would like to hear the rest of the story. Everybody claps. So he remained seated. He was piloting a 4-engine Air Force plane out over the Pacific. There was a plane 20 miles ahead, radioed back. There's a saucer, take a picture, heading their way, of course. So they had the cameras, and they took pictures. They called the base to which they were going, because they don't handle the film. That's intelligence material. Has to be taken off the plane by the guys with the clearances for that stuff. Some people think the pilot takes it to the drugstore. No, it doesn't work that way. They got debriefed and got told never to say anything. And I'm sure there wasn't anybody there who thought that I'd set this up, because I hadn't. The guy was obviously sincere and he wasn't looking for anything. He was being honest. Most people are. Give them half a chance. So I've been through this routine. And people are all surprised. And incidentally, the biggest reason when I asked, how come you didn't report it, they think I was some kind of a nut. And that's the most common belief. Any other questions? Who's going to the concert tonight?
Who's playing?
I don't know. Who's playing? What's the name of the concert tonight?
Something Del Muerto.
Oh, Due to the Dead.
Due to the Dead.
Due to the Dead?
Don't ask me what that means. I don't know.
I can give you a little brief history. It was started as a Halloween event.
Obviously.
And what they soon discovered is the folks that are our age are got kids, and they want to go trick or treating. So Charlie and I got together and said, "Well, why don't you just move it up a week so you know the parents will be free?" And so anyway, that's why we're having the Due to the Dead. And in comparison, if websites are any indication, last year he got 300 hits on his website. As of today, he's well over 5,000 hits. And there's a lot of people out there, a lot of good music, good food. And so join us. As tired as we are, we're going to the Due to the Dead concert. And you know, it's kind of funny because we went last night after we went to Okinaga. And we just kind of got like a second wind once we got out there, feeling all the energy that all the people were putting off. And we looked down our watches at 1 o'clock and said, man, we better go and get some sleep. But we wanted to stay longer. So anyway, it'll be a great show out there tonight. They have a lot of local bands, and not so local, but they're all local. So anyway, come out and have a crazy time at the Due to the Dead.
Before you leave, buy one of my books and I'll autograph it to you personally. Thank you so much.
And I might as well pitch this. We'll give you a few more minutes and we'll wrap up the silent auction. I hope you're here. So you see something you want, add $1 to it or whatever, and that's what helped us keep this thing free. I know that in a lot of places, this is a big ticket item, believe it or not. So anyway, we appreciate your participation in the silent auction. So go out there and if you're, like I say, unless there's 2 people standing at the same prize, we'll go ahead and take care of that right now. So thank you very much.
Thank you.
Go ahead with those.
That was pretty much a wrap.